Everyone, September 20th. So I did the interview today. Overall, it went pretty well, I think. No JavaScript questions at all. I mean, we're just regular LeetCode questions. So I just picked Python. So blew through. Okay, I got a little bit stuck on one of them, which was quite rare because all of them are quite easy, I think. But I guess just the nerve got to me. But anyway, that's not the point. The point is all the preparation for the JavaScript didn't really pan out. But I think that's still good to go through that kind of intensive learning about all the special features or headaches of JavaScript. So now they're all open, I think I will go through them no matter what. Okay? So like, it's okay, I'll go through them. Doesn't matter. Anyway, let's get to this. I know this question. I've done this a couple of times. Shouldn't be too bad. Oh, actually, no, that's not what I had thought. I thought it's to find the medium of two infinite arrays. This is the medium of two sorted arrays. Okay? Given two sorted arrays of size m and n respectively, return the median of the two sorted arrays. What is the median of the two sorted arrays? Ah, that's 2. Ah, I see. So yeah, the easiest solution is you do a merge sort and you find the median, right? But this wants you to do this, which means some sort of binary search is needed. What do you think? So we have two arrays, right? Basically, we want to know the median. That means when we apply the two together, what is going to be. How about we just say we guess a median and see if it is median? How would you do that? Well, if you do the guesswork, I mean, we know the smallest, we know the largest, so we guess a middle one, and then we put in the nums1 with binary search. So we count how many is on the left, how many is on the right, and we do a binary search on nums2. We know how many is on the left, how many is on the right, and then we add them together and see. But the problem of this approach is, all right, so first of all, we have to find out if the total number is even or odd, okay? If it's an odd number, then there got to be a match, right? If it's even number, that's a little bit tricky, okay? If it's even number, that's a little bit tricky. So we have two arrays, okay? So we say A1, A2, all the way to AN, B1, B2, all the way to BN. We don't know them, right? And then we can pick every time we pick a mid of the smallest and largest, we pick a mid. We say, okay, let's guess this is the median. And I binary search here, right? On the first one, binary search on the second one. Then we count how many is in the front, how many is in the end, and that way we can decide if it's a median. So if we have odd, then we know the median must be in nums1 or nums2, right? It must be in one of them. So when you do binary search, it has to match, right? It has to match. Like if I don't have a match on both, that means it's not gonna work. However, we still need to count, right? We still need to know if this value is too big or too small. Because if we put them together, there will be a median, right? So if it's kind of big, yeah, because we're counting how many is smaller than this value, how many is bigger than this value in total. So if it's median, so the number of smaller and the number of bigger shall be the same. But if we find such a value, and a number of smaller and a number of bigger, so on this one I can count number of smaller and number bigger, this one can count number of smaller and number of bigger. So we add them together. If we have too much smaller, that means it's too big. So we search again, right? So eventually we're gonna hit a point where we have the same number of smaller and the same number of larger. Okay, but let's just say it doesn't match. It's just we have same smaller, same larger, same smaller, same larger. So when that happens, what do we do next? Basically, we have a bunch of A1, okay, we can say to AK, and then B1 to B doesn't matter, and then we have AK plus 1 all the way to AN, B this plus 1 all the way to B, and doesn't matter. And then we have the current mid, right? So these are smaller, bigger, smaller, bigger. And the sum of this, the count, equal to the sum of this account. Okay? But we're not sure if this is. But once that happens, right? Oh, that's actually not going to be possible for odd. No, it's not going to be possible for odd, because for odd, so I think for odd, it's not going to be equal. It's going to be missing by 1, right? It's going to be either the left is 1 more than the right, or the right is 1 more than the left. So that's the case when we shall stop. So when we find that, let's just say left is big. Okay, so we have 1 more on the left hand side. So this has 1 more on the left hand side. And then here. So when that happens, we get out. Okay, we get out. And we know that the median needs to be either this one or this one. So we shall pick the bigger of these two. Yeah? If it's on this side, then we shall pick the smaller of these two. That is correct, right? So if we have even count, so eventually we'll find it's equal, right? It's equal. Then we find this and this, take the average. All right? It's definitely not a win, and we can give it a shot. All right, let's do this. So int low shall equal to math.minimum nums1 0. Ooh, look at that. It could be 0. Darn. All right, so we need to do some stuff first. Okay, so if nums1 dot length is equal to 0 and nums2 dot length ish. What the hell? Length is equal to 0. So both are 0. We shall return. I'm not sure. 0? What if both are 0? What do we return? Oh, they will not be both. Oh, okay. So I guess, yeah. So if this is equal to 0, then it should be nums2. And how do we do this? Well, we say if nums2 dot length is odd, right? Then we return nums2 dot length divided by 2, right? So 3 divided by 2 is 1, so that shall be right. Otherwise, we'll return nums2 dot length divided by 2, like 4 divided by 2 is 2, so 0, 1, 2, and we need to do this minus 1. So plus nums2 dot length. I wonder, No, I don't have to wonder. I don't think, because we need the small of the two. Yeah, I think it's better just to, get rid of this. Divide by 2 minus 1. Okay? So we'll do the sum of these and then divide by 2. Does that make sense? 2.0. Yeah, it makes sense. So again, so that's that. And we have to do exactly the same thing for the other case, which we just swap nums 1 with nums 2. Swap this nums 2 with nums 1. Right? Duplicate code. Yeah, I'll let it pass. Alright, otherwise we are going to do nums 2 0. Okay, int high will be math dot high. No, max. Nums 1 0 and no. Nums 1 dot length minus 1. Nums 2 dot length minus 1. Alright, I'll oblige private double get median int nums. Yeah, I'll oblige. So all the nums 2 will turn into nums. Okay, so we can say if this, I will return get median nums 2, and then if this, I'll say return get median nums 1. How about this? Okay, looks nicer. Wait, maybe I don't even need if it's in a single line. Yeah, I think in a single line I don't even need it. Now we do this. Okay, we have low and high. Then we say while, low smaller than high. It's okay. And we need to count. Right? Then we need a Boolean value. Is odd. Is total odd. So equal to nums 1 dot length plus nums 2 dot length mod 2 equal to 1. Okay, so while low smaller than high, okay, and we'll deal with this later. So once someone can say float. Oh, let's just do double mid. Let's put double here. Okay, double mid. Then we can say mid equal to low plus high divided by 2. Okay, then we need to do binary search. How do we do binary search? I do not remember. Java binary search. It's not algorithm. I just want to know what data structure to use or whatnot. No, come on. It's not what I want. You gotta be kidding me. It's not algorithm. There we go. That's the one. The binary search. returns the index of the found item. So by default, the method uses the first index of the array as a starting point. I know that. Okay. What doesn't find the element? If it is contained in the array within the otherwise minus insertion point. So I want the insertion point to define as the point at which the key will be inserted. The index of the first element in the range greater. So the index of the first element in the range greater than the key. Or to index if all the elements What if it's equal? Yeah, that's the thing. What if it's what if everything is equal? Because they didn't say that they're Yep. How do you handle if it's equal? Like if I have a stretch in the middle, and then, well, find the insertion point. That's supposed to make sure what the insertion point is. So, oh, hold on. If it's equal, which means if it's found, turns the index of found item and not the item itself. The first index. Nah, this is not. Do I have a array.binary? I need to go to array.binary search. There we go. Guess it's fine. We just search the search array. If the array contains multiple elements with the specified, there is no guarantee which one will be found. This method can. Oh shoot! There's no guarantee. We might have to roll the binary search ourselves. Holy crap! Holy crap! Yeah, we might have to roll it ourselves though. Because I'm thinking about binary search, right? But if you do binary search, if you have bunch of values the same, then what? That's an interesting question. So binary search, you find somewhere, so it's like bisect left or bisect right, and then you try it. Oh, it's interesting. Yeah, if you have duplicates, it is interesting. What do you think? Yeah, what if you have multiple duplicates? You binary search. Well, I mean, I can, let's say, do a binary search. We can do a specialized binary search. So let's say this will return a range. And then we do a binary search on the other side, or return a range. But if we return a range, how are we going to... Yeah, the range is hard to reason with, right? The range will be hard to reason with. Yeah, let's say we have a range, right? Let's say on this one we have a stretch in the middle, the same. On this one we have a stretch is also the same. So if a binary search, it is possible, if we are matching, it is possible to know what range we have, right? Basically in this one, the smaller or larger will have, so we have purely smaller, purely larger, okay? Then I need to implement, now we do the regular binary search, okay? We do the regular binary search, try to find something, you know, and these are all integers, right? Yeah, these are all integers. So maybe I can artificially not find the real thing. I artificially look for something 0.1. So we'll always end up on the right hand side. Okay? We'll always end up on this side. And then once we have it, we go look for this one, right? To see, because now we have, let's say, bunch. Yeah, let's say we do binary search. If let's say if these are all 8, right? And it will search for, you know, 8.1 and 7.9. Just don't search 8. Okay, we search 8.1 and we search for 7.9. And because everybody is integer, so if I have an 8, then 7.9 will come here, 8.1 will come here, right? It's already surrounding one integer, right? Or surround one integer. Then we can count how many is in the middle, right? So we basically say, if this value, if that integer in between is gonna be the center value, what is it going to be? But is this gonna work though? If we do this search, and every time we'll find like a pivot, yeah, we basically will have a value in the middle, right? Or like we don't have, right? If 7.9 and 8.1, they are pointing to, they're searching coming to the same position, which means the current is not 8, let's say current is 7, and this is 9, and both will end in the same position, right? If it's on the same position, then we don't have a value in between, so we don't have a value, yeah, which is fine. And all we want to do, right? All we want to do is to find, let's say we have a range, right? And then we, on the other side is fine, it's just small and big. So we do this plus this, and this plus this, and then we say, and it's even, okay? It's even. So we want these two, if both are smaller than a target, that means it must be inside a target. We're done. Yeah, think about it. Think about it. All right? Yeah, if it's even, and then we have this is smaller, this is smaller. Then if one side is bigger, oh, what if one side is bigger? Let's say we have too many on the small side, okay? Too many on the small side. Then what can I do to, this is just make things more complicated. You know what? I don't like it. I want to rethink this problem. This is doesn't feels good. Let's see. B1, B2, B3, Bn. Okay, we have 2. How about we use, I don't know. How about we use index? We find the middle index. Okay? We find the middle index. Right? And then the middle index will, yeah, if it's odd, right? The middle index, we have a half and half. Go here, half and half, right? And this one we can binary search, right? Oh, we still have the same problem, right? Binary search. What if it's equal? Oh. Let's not consider that for now. Let's just say it's not equal, right? Then we have a left and right. Then we can compute the left and right, right? If it matches, then we're good. If not, then what? What's the next value is going to be? It's like it's too small, then we need to get a bit bigger, right? But how big do we get? Yeah, it seems like it is the binary search issue. It's just, I don't want to do a lot of analysis. I feel like if I do the idea of a 0.9 and 0.1, there's going to be a lot of analysis. Going to be turn of value in the first, turn of value in the second, and then we have to analyze. All right? Oh man. So like we all have, and even odd is also different. Okay, let's just do odd. Okay, let's just do odd. No, even. I think even will be easier. Right, let's just do even. So I binary search for a value, you know, something 0.9 and then something plus 1.1. Okay, so I binary search on the top, on the bottom. And if the index is the same, right, which is plus 1 minus this one plus 1 will be the insertion point. And I think the insertion point is the bigger, right? Insertion point is something that's bigger if it doesn't match, because we're never gonna match. Can have different values, so we're gonna do such a key is 0, so just this one plus 1. So it'll be minus insertion point minus 1. So plus 1 didn't minus, so 0 will be where you need to insert it. Okay, so 0 will be inserted, and this is where you're gonna insert it. Okay, which is fine. We'll insert 8.1 will be inserting here. It's okay. So in that case, if I find it, if it both return the same position, which is fine, then we can get a front, get a back, get a front, get a back. We do the thing. And then after we do the thing, we compare, right? If it's equal, then we know which one to look for. Actually, no. If it's equal, nah. If it's equal, then we know this and this, right? And this and this. Yes, then we'll get it. Right? If it's not equal, if it's too much in here, then we too much small, then we shift it a bit big. If we can do that. Okay. So now if we have a range, okay, a range, which means a smaller 0.9 we point into here, all right, and then the 0.1 we point into here. So we know there's a range in between. So we ignore the range. Okay, on this one there's also a range, and we ignore the range. So we do this and we do this, right? And then when we add them together, right? When we add them together, if both sides is small, right? That means we will have to get inside the range, right? Honestly, that might not be true, because on this side, let's say it's small. Yeah, we're targeting the same value, right? Yeah, okay, yeah. If we're targeting the same value, if this side is small, this side is also small, then the answer is just, it'll be the ones in the middle, right? It'll be the ones in the middle. Yeah, but if it's big, okay, if one side is big, if one side is big and the other side is small, then we do the same binary search trick, right? If the left is 2, then that means then we do the trick. Yeah, let's say we have 2 values here, okay? We have 2 values here, and then everything small plus everything small here is larger than half. Everything big here plus everything is smaller than half, right? Then we know the whole thing is too small. We need to get bigger. So now we're gonna move bigger, okay? Then it will be, yeah, that's the thing. it's, so you have all the small count, right? And we also have all the big count. And we have the duplicate count in the middle. So once we have this situation, we have the small count, we have the big count, and we have the ones in the middle. Then what we need to see is if this middle count, right? If, let's say, the small one is larger than half, okay? This is smaller than half. So in that case, there's too many small, which means my value is too big. So I need to, it's larger than half, which means even if I add all these, like, okay, if both are smaller than half, the answer is just in the duplicates. No question, right? No question. So if one side is larger than half, the other side is smaller than half, right? That means if I add all these to the half, it's not going to work. It's not going to work, right? So in that case, we just, we readjust. We put the high lower. It must be in the smaller part, right? So if this one is smaller than half, and this one is larger than half, if that's the case, then we have too many big ones. So we readjust as well. So you know what? This is not too bad if it's even. It's not too bad. We just have to handle some extra conditions. So what if it's odd? What if it's odd? What if the total number is odd? What if the total number is odd? We can use the same trick, but yeah, we have the smaller half, bigger half, and then we have the duplicate in type. There's a smaller duplicate and the other half. So if so this, what we want to do is to find maybe this one is different. No, we cannot. It cannot be different. So we get grab, so we have the small half and big half. So if both half smaller than, the half will be this, and we have the medium and have the other. So this is kind of the half, right? If this one is smaller than half, this part is also smaller than half. So it must be in the middle. That's also good. If this is larger than half, and this one is smaller than half, now it depends, right? Now it depends. If this is larger than half, this is smaller than half, we don't count the ones in the middle. Ooh, if we don't count the ones in the middle, well, it depends if we have something in the middle, right? Depends, because in the middle it could be 0. It could be 0, right? If the middle is 0, which means we don't have any, which is most likely it's going to be 0. You know what? I think for odd, it will be very good if we never match a value. No. You still have the duplicate to deal with. You still have the duplicate to deal with. Whatever trick we have a duplicate to deal with, right? And here is just saying that because we are trying to find a range, right? We're trying to find an integer, right? We're trying to find an integer, and then we're basically saying this integer has some duplicates, right? And then if on one side is larger than half, and if we don't find this integer, I think it has to be considered separately. If we don't find any integer matching the current one that we're looking for, then if it's larger than half, smaller than half, depends on if the larger half is one more than the smaller half. Okay? Yeah, it's one more smaller. And if it's not one more smaller, oh, not one more larger, that means it's just a lot larger, right? A lot larger. Then what? Yeah, then we have to shrink. I think it's, yeah, it is the same, right? It is the same. Because if the medium is really in the stretch, then you will find the stretch, okay? Then you get the left hand and the right half to all be smaller than half. If the medium is not a stretch, then you find a stretch. Then one side will be too big, and then you just have to redo it. Yeah, I guess it's fine, right? I guess it's fine. Okay, let's retry it. But we're doing this trick. We're doing this trick. So mid is gonna be double. Okay, so this is gonna be this mid. Actually, we have the mid left and mid right. So I have two mids. Okay, I have two mids. And we'll do, actually low and high is gonna be, let's put them as double. All right, low and high is gonna be double. So mid will be this, mid left, right, will be this minus 0.1, and mid right will be plus high divided by 2 plus 0.1. Okay, then we have index left, id left shall equal to nums1 dot now arrays dot binary search nums1 it might not even allow me to do it. Nope, it does not allow me to do it. Cannot resolve this method. I need to convert this into, oh. It forced me to write my own binary search. It's a mixed binary search. Dude, I'm trying to avoid doing this. Okay, that's fine, that's fine. So we can say private int mixed binary search. Okay, so we're passing in this, and it will be double v, right? And want to find where the v is going to be, right? So we have int low equal to 0, int high equal to nums.length minus 1, while low smaller than high, int mid equal to low plus high divided by 2. Okay, and then we say if nums mid, right, if it's larger than v, right, nums mid is larger than v, then high shall equal to mid. That's too big. We need to go to the left hand side. Else low shall equal to mid plus 1. So current one is too small, so it'll be plus 1. So eventually when we jump out, it's going to be low equals mid plus 1. Right? So whatever it is, low, which means nums mid is larger, is smaller equal to v, right? V is here is smaller, but it won't be equal to because v is a double, so it's smaller, right? Current is smaller than v, So now we plus 1. And then it matches, it comes out. So the one that comes out is something that's bigger than v. I think that's exactly what we need. We just return low, right? I think that's exactly what we need. What we get out is someone that's larger than v. I think that is exactly what we need. So I wrote my own, so I can say mixed binary search. We'll go nums1, right? And mid left. Int id left, int id right. Okay, so id right mixed nums2 mid right. Okay, so I got these two. Then what we need to know is the total on the left and the total on the right. Okay? Total on the left and total on the right. So we need to say total on the left and a total on the right. So on the left is going to be id left, because that is the index. Okay, that's index when it's bigger. So nums1 id left is something bigger than the mid left. Oh shoot, there are more. There's id left 1, mid left. So id left 1, dude, id right 1, id right 1, and id right 2. Gordy. So it'll be 1 and id right 1. So we mix this nums1 and mid right. And then this id left 2. So it'll be mid left. id left 2. id left 1. id left 2. Right? And id right 2. So mixed nums2 mid right. Yep. So now we do all that. Okay. Now we do all that so we can find the total that's smaller than the current integer. Okay. So we say gonna be id left 1 plus id left 2. That's the total number that's smaller. So we say if half, if this is smaller, we say int half shall equal to nums1.length plus nums2.length divided by 2. Doesn't matter even or not. So we say if this side is, it's smaller or equal to man, there's a lot of conditions. Lots of conditions. Handle the easiest condition first, okay? So no matter what, if this side is larger than half, okay? If this side is larger than half, which means we have too much, it's already more than half. So if this side is larger than half, regardless, right? Regardless what, we have more than half on this side. But now it depends on whether it's even or odd. Yeah, this just doesn't feel right to me. It's way too complicated. Way too complicated. Okay, let me just handle this. If is total odd. Okay. Yeah, I'd like to handle the even situation first. Okay, so now it's even. So if one side is larger, then the other side, the left is larger, then the value is too big, right? So the high shall equal to high shall equal to mid to the mid right. Oh, we say it's too big. So how about high equal to mid left? Now we need to keep low and high as integer. We have to. These has to be integer. Integer division. Does it matter? It does. It does matter. So I'd rather double it Okay, I'd rather double it. I think it's important that we keep this integer. Right, I think it's important to keep it integer. So, mid left. So maybe we can integer this. Man, it still feels too complicated. I still feel this too complicated. There's so many conditions to consider in this method. It doesn't feel right. Okay? It does not feel right. Okay, so what else do you want to do? We can say else if id right. I mean, it's a total count. It's not really id right 1, right? Because id right 1 is here. So I want to know, I think it can be nums 1.length minus this. That's the total. So 0, 1, 2, 3. Okay. 4 minus 2 is 2. Yeah, so it'd be this plus nums 2 dot length minus id right 2 if those are larger than half. That means we have too many, so it's too small. So we can say low equal to int mid right. Maybe mid right. Actually, if we think about integer division, right? We're trying to find this integer, and then we say it's too much on the left hand side, so this one need to go lower. I actually think this should be mid right. It's not mid left. I think this should be mid right, and this is mid left. Because for low, right, this low usually high equal to this, low shall be this plus 1. You know what? I think this is mid right as well. Both are mid right. Because low is going to be mid plus 1. Mid plus 1. So I say this plus 1. I think I will want to do it in equal. Or do I not do it equal? Too many moving parts. Too many moving parts. We have more, right? This is larger than half, or this one larger than half. Now both are smaller or equal to half, right? So if we do an else, now both are smaller or equal to half, right? Both are smaller or equal to half. Now that's the thing. Both are smaller or equal to half. If both are equal to half, or let's say one side is equal to half, so both are smaller or equal to half, right? Now if it's a mismatch, whatever thing it doesn't have, then so elif let's say if let's say if we don't have anything for both sides, so this one's a missing on both sides, and both are smaller or equal to, then they have to be equal to, right? Then they have to be equal to. Yeah, because it's nothing in the middle, right? If it's nothing in the middle, basically it's an integer that's missing. Then the answer shall be okay. But if one side has something, so it's smaller, this is also smaller, but we have something in the middle. Okay, we have something in the middle. And one side is smaller, the other side. Yeah, how are you going to handle that? I don't think it's right. I don't think it's right. It's way too complicated. It's way too complicated. Okay, I'm going to solve it using the stupid method. Divide and conquer. Divide and conquer. Huh. Are you divide and conquer right now? I'm not dividing and conquer. What do you mean by divide and conquer? Well, we can mean, because we want to find, we want to find a medium, right? We want to find a medium. That means we need to find a value. If it's odd total number, we want to find a value such that in the first array, yeah, the headache is the duplicate, okay? The duplicate is really, it's a real headache. Real headache out there. Make it really tough. Duplicate. M plus N. What if we do binary search, right? And as I'm doing this, it's a special version of binary search, right? And we find the middle. If it's smaller than that, then we say low or equal to mid plus 1. And then we do a middle. That'll be bigger. So high will be middle. Smaller. Yeah, this will converge, I think, on the right hand side this way. It's like the left. Yeah, it's not gonna work. Alright, it's been an hour. Still didn't have anything out of it. So what I'm gonna do is just do the stupid way. Probably leave these as is. We are going to do the stupid way. So I just want to kind of get it done. Okay, just get it done. So we'll merge sort. Okay, we'll merge sort. So we say nums int, right, merged okay, then we can say int I equal to 0, int j equal to 0, while I smaller than nums1 dot length and j smaller than nums2 dot length. Oh, we have a we need a k. Okay, k equal to 0. If nums1 I is smaller or equal to nums2j, merged k equal to nums1 I. Okay, then k plus plus I plus plus, else merged k equal to nums 2j, and then j plus plus. I just realized I'll do to k plus plus no matter what. So let's do k plus plus at the end. Okay, when we get out, we say while I smaller than nums 1 dot length. Oh, I can do a fancy thing here. We can say merged k plus plus equal to nums 1 I plus plus. Right? We do the k first. We do the k first and then increment. And we do the same thing. Say if j is smaller than nums 2, then this will be this. And then we'll return return what? Nums merged the length mod 2, the 1. We'll return merged the length divided by 2, right? 5 will be 2, 0, 1, 2, yeah. Otherwise, be something divided by 2.0. That will be merged the length. Oh, I can reuse this function, get median. Okay, get median, merged. Okay. Doesn't really work. I mean, this one will work because it's, you know, and then it will also work the edge case as well. What the hell? Index out of range. That's interesting. Oh, we do have to handle this. Good point. Wow. I thought we don't have to. Boy, am I wrong. That is interesting. 1.5. What the hell? The second one. Did I mess up with the merge sort? Actually, I can do plus plus. Right? I can save this line. I can do plus plus. Save this line, and I already done plus plus. Yeah, so this is smaller than this. I plus plus. This is smaller than this. I plus plus. So put 1, 2. This is done, and then we plus. What? Is that right? Let's just take a look. What the hell is wrong with this? Let's say system.out.print line array. Actually, I'm not sure. Merged.toString. Yes, we have this function. Merged toString. Okay, is this right? You gotta be kidding me. What the hell is that? What? I print toString. Dude, come on. All right. This is ridiculous. This is ridiculous. 1, 2. I mean, if I cannot solve it using a better method, this is a stupid method I shall be able to solve. But then I got these issues. Stupid. Absolutely stupid. Find nums1, nums2. Okay, now I'll do this plus plus. Because I just find this cool. I want to do it that way. Alright, I don't have to do this. And I want to print. Okay, let's say, yeah, exactly. It's like, oh, I don't have to print. No. There'll be better things right here. I just debug. Yes, debug. Okie dokie. I want to know the merged. Okay, give me merged. Right? 1, 2. You gotta be kidding me. What in the world? What in the world? 1. Okay. 2. That is good. Oh, yeah, it's right. My bad. It's right. 1 don't do. J can do. Oh, shoot. I don't know. Typo happens all the time. Really messed me up, man. And I think this one should be right. Right? And I have one more trick up my sleeve. I mean, we already at this point, right? So why not? Why not? Huh? You see what I'm going? Why not? Plus, I think if we do this, we don't even need this. We can say, then we do, then we do, Yeah, I need to find fun. Right? This is fun. How fun is that? I'm not sure. Tell me it's wrong. Okay. Variable expected. Yeah, I guess this is not allowed. Okay. Fair enough. Fair enough. Yeah, I think you have to assign something to something. I don't know. I guess it's just not allowed this way. But this is good enough. Right? This is good enough. Oh, no. We can do it. We can. Right? We say this, and we say merged. No. Put it here. Merged k++ shall equal to. There we go. Now we're talking nums 1i++ or nums 2j++. Right? And then we don't need this. Look at that. And then remove and remove. Look at that. 5 lines, right? 5 lines. Okay, so let's do this. Man, I haven't written something like this for a while. Didn't fix a typo, man. You're stupid. Didn't fix a typo here. Alright. It'll be slow, but it will get the job done, right? Merge sort will get the job done. But this is definitely not the ones that we want. But I really have no idea how to get the other one. Alright, let's just put this in. So we call it solution 1. Now this is the dumb one. Dumb solution. On, not the required O log n plus n. But we get the problem solved. So now we start thinking about the good one. So how do we do this? How complicated is the binary search? Hey, it's not as complicated. I knew it, right? It's not gonna be that complicated. So the way I'm thinking about it is definitely not right. Oh, hold on. This is not binary search. This is a merge sort. No. I want the binary search. Is it complex? Oh my god. Oh my lord. Dude. Yeah, but the overall is not that bad. Yeah, it's divide and conquer. It's n plus n. N plus n. Alright, how do we divide and conquer? Yeah, I know it's binary search. Here we use binary search to find target in sorted A. Locate the middle index. Using index. Compare the value of the middle element with target. Reduce the search space by cutting the current array in half and discarding the half which is guaranteed not to contain target. Repeat the above until either we empty the array or we find target. Okay, this is just a regular binary search, right? So at each step, the search space is cut in half, so we can quickly get the result. Now back into this problem where we have two arrays, okay? We got A and B. Then we can get the and compare their middle value. Let's say A mid is smaller or equal to B mid. Okay, that's fine. This implies that we can compare sections of A and B. We use this to represent the relative magnitude of values. For example, this means that every element in A left is no larger than any element in A right. If this is smaller or equal to this, that means everything here, not necessarily true, because I can have like 2, I can have 1. A left. Every element in left is no larger. Okay, this is correct. A left is smaller or equal to this. B mid is smaller. That's correct. Combining these two observations, so we can say A left smaller or equal to this, smaller or equal to this, smaller or equal to this. That is correct. Thus, A left is smaller or equal to this. That is correct. Okay. Now we know that A left is smaller than 2 halves. This is smaller than this half and this half. Although we still don't know where exactly these elements are. What we do know is A left doesn't intersect with A right plus B right. That is correct. There is an invisible boundary between a left segment and the mixed segment of these two. A left, So, okay, let's not read this. What insight can you get just by reading that? So A left, so we know, so by doing this, we know the total count. I'm still having this total count idea, right? So I have the total count on the right hand side, right? If the total count on this is bigger, okay, than the half, because at the end we're just looking for half, right? If it's bigger than a half, that means the median must be inside this branch. It cannot be on this branch. Well, but I mean, we start with the middle, so the count is actually the half. Yeah, that's not it. All right, that's not it. All right, let's keep reading. I don't think it's the count. All right. The following step is the most important one. We're looking for the median sorted A, which is one or two target values. We regard the index of the target value in the sorted as k. For example, if the length of A and B are at 6 and 5, then the target is 6. Target index is 6. We should look for the 6th smallest element. If the length of our 6 and 6, we should look for the 6th and the 7th smallest. That's good. Depending on whether the total number of elements are odd and even, we need a kth and maybe the k plus 1th elements. What matters is that we set an index k at the beginning, and we want to find the kth smallest element using binary search. The kth, we want to find the kth or k plus 1th smallest element. So by doing this, right, we have found, no, we never found anything, but we do know that this one is smaller than everybody else, right? This one is smaller than these and these. So this is we know this is smaller, but is that the smallest? Is that a kth smallest? Keep reading. During a binary search like algorithm, we keep removing 1/2 of the array, so the index k might not stay unchanged. Suppose we removed 3 elements that are smaller than the original kth smallest element. We shall take the k minus 3th smallest element from the remaining arrays. We remove 5th smallest element. We remove the smaller half of A that contains 3 elements. We're now looking for the 2nd smallest element. What if these are the smallest, right? If k is larger than half the total number, if k is larger than half the total number of elements, it means that the kth element hold on. If k is larger than half the total number of elements, it means the kth element is in the 2nd as a larger half. Does A left or B left is guaranteed to not contain this element? Hold a second, let me read this one more time. So what it's saying is, if the kth smallest, right? If the kth smallest is, let's say it's odd, okay? So the kth is actually in the middle, right? But in this one, we say A left is smaller. Yeah, so we want to find the kth smallest value. If it's for the entire thing, okay, for the entire thing, then what we can say is these two will definitely be bigger than half. I think that's kind of the point, right? They will be bigger than half. Now, if they are bigger than half, and if the k is larger than half, then it must, if the k is smaller, if k is larger than half, then it definitely does not exist in this part. Because this part is smaller than this, smaller than this, and then smaller than this, smaller than this, right? And we know the target will be larger. A left smaller equal to A right. Yeah. A left is smaller equal to B right. Yeah. So now you're saying if it's larger than half, yeah, because this is smaller than this, right? Which means everything here is smaller than this. There might be something smaller here than this, but everything will be smaller than this. Then we say we want to find a kth largest. If the kth largest is existing here, and the k is larger than half, so basically we'll ask, is this going to be the kth largest, is the one in the middle? It's not going to be the kth largest because I have this added together, right? So this added together, if it's already larger than k, then a kth, then we have less than k on this side. So it would definitely not be inside here. It could be in here. It could, but it could not be in this part because this mid is not the kth largest, right? If it's odd, then we have these two added together, and now plus 1, right? So this is definitely not the kth largest. Oh, depending on what you define the kth largest. I think the kth largest is more than half. Is more than half, right? It's more than half. So if it's more than half, then it has to be this one, right? And the most is this is the kth largest, because this is definitely not kth largest. Right, because the kth largest has to cross the half line. Cross half line. So we have half on this side, so we have half on this side. And the kth largest shall be the bigger one. So this cannot be. That actually makes sense. That actually makes sense. How about even? In the even situation, if this is even and this is even, then we pick a half, right? Be to the right side of the half. This is, I'd like to say it's the same thing, but if k is larger than half of the total number of elements and sorted, it means that the kth element is in the second half. Thus A left or B left, the smaller of the two according to comparison, is guaranteed not to contain this element. And reduce k by the length of the removed half. If k is larger than a half, then we have a smaller half. Yeah, because every time we find a half, right? Every time in the array, we find a halfway point. We find a halfway point. So if the required is going to be larger than half, right? Because when we find a halfway point, we always have the larger half plus 1. So if it's larger than half, then yeah, it's not going to work on the smaller one. So if it's smaller than half, right, then the bigger one's not going to work. And we can safely discard it. Note that we don't need to modify k this time since we removed one larger half. So k stays the same, right? So the kth smallest. So yeah, we just need to find if the kth is, but you say the half the number, right? Half the number, what if it's even? That's easy to say. Larger than half the total number. Okay. Smaller than half. Yes. No, we'll use index. Yes, 4 pointers. But this half thing, I'm still having doubt. What if, I mean, this is odd, right? What if the total is odd? Which means, what if I have something like this? I have, let's say, 5 on the top. 1, 2, 3, 4, and then we have 4 on the bottom. 1, 2, 3. So I find the midpoint is here, and the bottom 4 means 0, 3. So we'll find this is the midpoint, right? And then we find the two midpoints, then do the comparison. Okay, so we know which one is the shorter side. In that case, if we're looking for the kth, and then added together is odd. Divide by 2, right? Divide by 2. So if you think about here, the bigger side has 1, 2, 3, 4, right? I have 4 on the bigger side, and I have 3 on the smaller side. So we say if the k is larger than half, nine divided by 2 is 4. Well, actually, if you half is 1, 2, 3, 4. 1, 2, 3, 4, right? Total count is 9. Divided by 2 is 4. So if the kth, right? If the kth is larger than 4, doesn't touch 4, so you'll have to go on the right hand side. That doesn't make sense. I think it doesn't explain this one well. The edge case. I don't understand the edge case. We want to find the kth largest. Yes, we want to find the kth largest. We want to find the kth largest. And in the start, I just want to know if it's like in this case, where's the kth largest? Suppose it's larger than half or smaller than half? Because half is 4, right? And then we want to find 4, so it's equal to, right? It's equal to half. Yes. What if it's equal to half? If it's equal to half, I mean, this case, if it's equal to half, we have like half here plus this, because these are all bigger, right? So it will not be on this side. It will not be on this side. So I can throw this side away. Yeah, because we have basically this, all of these are bigger than this, right? So we have at least more than half is bigger than this. And the same thing, we'll have at least more than half, it's smaller than this. Okay, I'm convinced. Then you have to code it, right? So I have to do this. Yes. So we need to find a mid first. Find a mid. Get the middle value of the two ranges. Get the middle value of the two ranges, A value and B value. Cut one value in half. one array in half according to if A index plus B index is smaller than K, A index and B index. A index and B index. If A index plus B index is smaller than K, which means K must be on the right hand side. Right? If A is smaller than B, we cut the small. Otherwise, we cut this half. Otherwise, we cut the larger half. If this is larger equal to K, which means K is going to be on the left hand side. Two middle elements. Yeah, they're both a lot of lines. Oh my god, there's a solution 3. Gosh. I thought that was it. Alright. I mean, we don't have time today anyway, so I'll just leave it be. I guess I'll implement this tomorrow. We have so many tomorrow left. Jeez. And then I have to do this other binary search. What? Ugh. It is torture. Alright, that will be it for today. I'll see you guys tomorrow. Adios.